July 25th, NASA's most ambitious Mars flyby campaign was in full swing until a set of leaked images of the interstellar object 3I Atlas triggered an unprecedented emergency shutdown. Within hours, a secret advisory paused millions in scheduled experiments, blacking out all further observations. The official story says it was a data integrity review, but insiders hint at something stranger, a discovery so unsettling it forced NASA's hand. If these images revealed a truth too dangerous to share, why has every trace been buried? What secret could possibly justify halting a mission this big, this fast? The answer starts with the leak and the chaos that followed. The first file drop hit at 0207 UTC July 21st, 2025. Not an open science archive, not a press release, just a string of encrypted uploads on a secure internal communications channel, visible only to a handful of NASA and contractor accounts. The file names were generic, but the metadata told a different story. Exposure times, filter bands, and instrument IDs matched the Mars flyby campaign's most sensitive observing blocks. Within minutes, IT security monitors flagged the transfer. Chain of custody routines kicked in. By 0224, the alert had escalated from a junior analyst in Houston to the agency's incident response lead. Internal chat logs later referenced in off-record interviews describe a scramble. System lockdowns, user credential audits, and a rapid-fire string of pings to project scientists on both sides of the Atlantic. The files themselves were ordinary at first glance. FITS headers, standard calibration frames, nothing obviously doctored, but the timestamps lined up with a block of images that, according to the official schedule, shouldn't have been processed yet. Someone had bypassed the embargo, pushing raw data before the principal investigators even finished their internal review. The communications channel, usually reserved for routine handoffs, was suddenly a hot zone. Every download, every access attempt, every hash check left a digital footprint. Forensic protocols demanded a full trace, but the sheer speed of the escalation left gaps, brief windows where it was impossible to know who had seen what or whether copies had slipped out before the lockdown. By 0232, a freeze order landed. All ongoing experiment blocks referencing 3I Atlas were suspended. Remote observatories received a halt signal. Automated scripts cancelled scheduled uploads. The advisory cited data integrity concerns, but the language was sharper than usual. No press statement, no public-facing update, just a cascade of redacted emails and a silent blackout across the project's internal dashboards. The reaction wasn't routine. It was the kind of digital dragnet that usually follows a breach, not a simple scheduling error. For the staff caught in the crossfire, the message was clear. Something inside those images had triggered the highest level of institutional alarm. The question whispered in private threads and encrypted texts was simple. What had they just seen? And why did it demand absolute silence? The freeze order didn't just stop a single data transfer. Within hours, the entire Mars flyby remote sensing campaign was scrubbed from the October schedule. Project managers received an internal advisory flagged data integrity review, stamped with the kind of urgency usually reserved for hardware failures or planetary protection events. The language was deliberate. No mention of leaks, just a directive to halt all experiment blocks referencing 3I Atlas until further notice. Teams at JPL and the Planetary Defense Coordination Office were told to stand down. Observation windows, some booked years in advance, vanished from shared calendars. Instrument time on Mars orbiters, considered the most valuable resource in planetary science, went dark. The lost observation block was more than a scheduling hiccup. Weeks of coordinated spectroscopy, planned to capture 3I Atlas as it threaded past Mars at 30 million kilometers, were erased. For mission schedulers, the fallout was immediate. Experiment proposals frozen in draft, data pipelines rerouted, budget lines flagged for review by oversight committees. The October campaign had been set to deliver the only close-range spectra before the object slipped out of range. Now the opportunity was gone. Internal memos circulated with clipped phrasing. All personnel are instructed to suspend data acquisition and refrain from public comment pending outcome of the review. Principal investigators, many with careers riding on this dataset, found themselves locked out of their own projects. For some, the blackout meant months of work, reduced to a string of error messages and revoked credentials. For others, it meant a scramble to justify lost grant dollars and explained to international partners why the campaign had evaporated overnight. The shutdown left a vacuum. No press release, no timeline for resumption, just a waiting game enforced by layers of institutional caution. In the absence of answers, speculation flourished. The only certainty was the silence, a silence that stretched across continents and time zones, enforced by the weight of a single unsigned advisory. What exactly needed reviewing inside those images remained off-limits, even to the people who had captured them. The first flagged images of 3I Atlas didn't just show a comet streaking through space. They captured something that stopped the survey team cold. A tail so sharply defined, it looked drawn by a straight edge stretching in a perfect sphere behind the nucleus. Not the usual diffuse cloud, not the tangled plume of dust and gas you'd expect from an icy wanderer. The length-to-width ratio was off the charts, narrower and more collimated than any comet tail in the Minor Planet Center's archives. For a moment, the team at the Atlas control room wondered if they were looking at a processing glitch, but the symmetry held up frame after frame across multiple filters and exposure times. Then came the glints. In several exposures, pinpoints of light flared along the object's sunward edge, brief mirror-bright spots that didn't fit the scattering pattern seen in natural ice or dust. These weren't cosmic rays or hot pixels. The highlights appeared and vanished in sync with the object's slow rotation, lining up with the geometry of the tail and nucleus. Raw pixel values spiked in a way that suggested not just reflectivity, but concentrated metallic reflection, hotspots that, if plotted, mapped out a grid of facets across the surface. One analyst, staring at the histograms, muttered that it looked less like a snowball and more like a polished shard, tumbling through sunlight. AI-driven surface reconstruction, run as a routine check on the data, only deepened the confusion. The generated model didn't spit out a lumpy, irregular body. Instead, it hinted at flat planes and sharp transitions, facets that caught and bounced light with uncanny precision. The machine flagged the surface structure as an outlier, unlike any comet in the training set. The word unnatural started circulating in the logs, half joking at first, then with a nervous edge. Metrics poured in. The tail's collimation held steady at a ratio of nearly 12.1, tighter than any recorded in the last decade. Reflectivity spikes measured more than triple the average for carbon-rich or icy bodies. Even the distribution of the glints suggested regularity, clusters spaced at intervals that didn't match random outgassing or dust ejection. The more the team scrutinized the frames, the less they could explain away. Inside the control room, the mood shifted from routine curiosity to something close to alarm. One senior observer with 30 years of comet imaging behind him quietly closed his laptop and walked out. Another started drafting a message to the project lead, her hands shaking as she typed. The images were already being copied, hashed, and uploaded to secure storage, but the sense of control was slipping away. If these patterns held up under laboratory scrutiny, the object in those images wasn't just another interstellar visitor. It might be something the textbooks weren't ready for. Spectroscopy doesn't care about appearances. Strip away the drama of a sharp-edged tail or mirror-bright glints, and what's left is a set of numbers, wavelengths, absorption lines, the chemical fingerprints of whatever sunlight touches. At Harvard's Center for Astrophysics, the first reduced spectra from the Mars flyby block landed in the early hours of July 21st. The team's lead, a professor with decades of comet analysis behind her, ran the pipeline herself. She expected water, carbon dioxide, maybe some trace organics. Instead, the spectrum told a stranger story, the most prominent feature, a broad, shallow dip centered just above 1 micron. That's the region where nickel leaves its mark, an absorption line familiar to anyone who's catalogued metal-rich asteroids, but out of place in a comet. The data were clean, no cosmic ray spikes, no calibration drift. The AI denoising routine trained on thousands of comet spectra from the last decade flagged the band as an outlier. It labeled the fit as low-confidence non-cometary signature. Ordinarily, dust bands dominate this part of the spectrum. Silicate grains and carbon compounds scatter light in predictable ways, creating a forest of shallow valleys. Here, the ordinary dust signature was missing. Instead, the absorption was too broad, too smooth, too deep, matching nickel, not amorphous ice. The team ran the spectrum against every known comet in the Minor Planet Center's archive. Nothing matched. Even the notorious outliers, like the carbon dioxide-rich hyperactive comets of the Oort cloud, showed the expected dust slopes. 3i Atlas did not. MIT's data group, running an independent pipeline, got the same result. Their AI flagged the same 1-micron anomaly and found no trace of the classic water ice band at 1.5 microns.